In this video, we'll go over Le Chatelier's principle, and we'll look at some of the effects of temperature and pressure on equilibrium, as well as one last practice problem. Okay, so Le Chatelier's principle states that if stress is applied to a system that's already in equilibrium, the system will adjust to relieve that stress. Okay, so let's look at an example. So here we have two SO3 going to make SO2 and O2. And if it's already at equilibrium, which is important for applying to Le Chatelier's principle, so this applies to systems at equilibrium. So if the system is at equilibrium and we add O2, what is going to happen for this reaction? Will things proceed to the right, the left, or will there be no change? Yes, so this reaction will proceed to the left. Here's how I like to think about these problems. So if we add O2, that means we're going to increase something on this side. We've now shifted the balance with an increase. So in order to fix this and decrease it, we have to go to the left. Okay, so what would happen if we removed SO2 at constant volume and temperature? Let's go back and look at all of these. So if we remove SO2, this is going to go down. And now there's not enough things on the product side. And so in order to fix that, we're going to have to fill in the deficit. And so the reaction will proceed from left to right. Okay, so let's look at how a few other things might affect some of these systems. So how about this one? We have magnesium hydroxide, which is a solid, and we have magnesium and hydroxide, and what's going to happen when we add HCl. So when you're thinking about this, think about what might happen with HCl and if it can react with anything in this solution, right? So if we just added HCl and it wouldn't do anything in this equation, adding it here wouldn't affect the equilibrium. But does HCl react with something? We look at these species, and maybe you'll remember that OH minus is a base, HCl is an acid, and an acid and a base will definitely react to completion. So what that means is by adding HCl, it'll react with the OH minus to make water. And so effectively, adding HCl will reduce the OH minus, and now we've created a deficit, so this reaction will proceed to the right. And when we look at this expression, we can see this is a solid magnesium hydroxide. Wouldn't appear in the equilibrium expression, but we're still going to change the equilibrium by adding the acid. But an important thing to note here is what we've effectively done. This is a really small equilibrium concentration. By adding HCl and helping it proceed to the right, we've made it a lot easier to dissolve the magnesium hydroxide. This is why a lot of cleaning products and things like that often contain acids. The acids can react with a basic salt to help them dissolve, and then you can flush it down the drain with just some more water. Okay, let's look at another thing that can change the equilibrium, and we'll think about temperature. So let's look at water and the vaporization of water. So if we have liquid water and gas, we saw this equilibrium before. We can think about which side of this equation heat is on. So think about this for a second. If you have some water and you heat it up, does it turn into more liquid or does it turn into steam? And you know the answer for this. If you add heat, you get more gas. So that means if we put heat on this side as a reactant, adding heat to the liquid water will give us more gas. Since heat is on the left side, now we can actually think about what will happen. So if we add heat, we've made more things on one side of the reaction. To relieve that stress, it'll have to go to the other side and make more gas. This is also another way to check to see if you added on heat on the correct side of the reaction. If you know that heating something up will cause the change, you can do it just like this, what we did with the arrow. So adding heat pushes it to the opposite side because heat is a reactant in this case, and it should make more gas. So this is consistent with what we know. Heating up water will also tend to make it boil more, or we'll get more steam. Something important to note about this is that temperature actually changes the value of the equilibrium constant. So everything else that we've looked at in this whole section won't actually shift the equilibrium constant. The equilibrium will change, but the value of K won't change. Changing temperature is the only thing that we'll talk about that actually changes K. And in this case, since we know it's shifting to the right, that means we're being more product favored. And remember, product favored means a bigger K. So in this case, we'd actually be increasing the value of K when we increase the temperature. So remember, again, the equilibrium constant is going to be constant as long as temperature is constant, but if it changes, the value of K may change. Okay, so here's another example where we have an equilibrium, and here's the equilibrium constants at different temperatures, and we have to think which side of the reaction is heat on. Okay, and the correct answer for this is the right side. Let's think about how this happens. So here we've increased T, and we can see that lowered K. So that means if we raise the temperature, a lower K means more reactant favored. And so if we are lowering K, that means we're shifting towards reactants. And for it to shift this way when adding heat, heat has to be on the right side of the equation. Let's look at what happens when we change volume. So here we have an equilibrium with several gases, and we can look what will happen when the volume is reduced at constant temperature. When you're thinking about this, remember PV equals nRT, and if this is constant and volume goes down, what's going to happen to the pressure? Okay, and so we'll see the equilibrium of this will shift to the left. In order to see this, we need to think about what's going to go on here a little bit. So if the volume is decreasing, for this to remain constant, the pressure will also have to increase. And since these are all gases, that'll affect all of those. Now, we have gases on both sides, so it's going to go up on every side of the reaction. Here we have 2 moles of gas. Here's 2 moles of gas. But over here is actually another mole of gas. So you can see it's going to increase the product side more than the reactant side. So this is going up by a lot. This is going up by not quite as much. And so to restore the balance, we would have to proceed to the left. And so here's a summary again of what we did. Reduce the volume, saw how it's related to Kp, and then we saw this relationship between pressure and volume. Here we can look at this again, these changes in moles, and we saw the shift to the side with fewer moles. So this is also another way to think about this one. If you don't want to go through all the arrows in the case of the gases, you can just think about the situation where we're reducing the volume. We're putting pressure and we're squeezing a system tighter than it was. And so in order to reduce this pressure, you can reduce the moles that are inside of it to relieve the pressure. Okay, let's look at one other thing that might affect the reaction. In this case, what would happen if we added a noble gas at constant temperature and volume? The answer to this is nothing. So remember that this equilibrium expression is going to depend on these partial pressures. So we have the N2O4 and the pressure of the NO2. Now in this case, adding a third gas, as long as we keep temperature and volume fixed, we will be adding more moles, so it'll change the total pressure, but these are the partial pressures of the individual gases. And if you might remember Dalton's law from the gas laws, the partial pressures are independent of each other for the individual ideal gases, so changing a noble gas won't actually affect the partial pressures of these, and hence there'll be no change on the actual equilibrium in the system. This will be true in any case if we add something that's completely unreactive in a system that is at equilibrium. This is just an overview of one of the applications of equilibrium. So this is how we produce NH3. This is the equation we looked at the beginning of the system with heat. This reaction is actually super duper important. Back in the day, there was this prediction that eventually we would run out of food, like the Earth wouldn't be able to support the population. And that was a population a lot smaller than we have now. Of course, that didn't come true. We have plenty of people, and while there's still food problems, we produce enough food to feed the population. And a lot of this was actually overcome not by the predictions being wrong, but by good science finding a solution to the problem. So this reaction here, fixing nitrogen, is very important to make fertilizer, and the fertilizer that we use to grow a lot of our food. This process accounts for about 1% of all the energy used in the world. It sounds like a small number, but when you're thinking this one process uses that much amount. The problem with this equilibrium is because heat is on the product side, normally you'd raise the temperature to make a reaction faster so that we could make this ammonium fast enough to make enough food, but it's going to reduce the equilibrium, so it'll push it the wrong direction. However, if we look at the number of gases, we can help push it to products by increasing the pressure. And another thing we can do is constantly skim off the NH3 to keep pushing the equilibrium to the right. So this whole setup is designed to do these two things. Okay, so let's look at one last equilibrium practice problem. So here we have a reaction at equilibrium. We have a certain pressure of NO2 is put into an otherwise empty vessel, and at equilibrium we have that 35% of the initial NO2 remains. We want to find the initial pressure of this gas. So for an equilibrium system, we have some initial pressure, we have an equilibrium pressure, so we probably want to set up an ice table. So there's our N2O4, going to make 2NO2, and there's our ice table. Okay, so initially we have some amount, it's not telling us, of NO2. We don't have any of the N2O4. Since we don't have any of the N2O4, we know that we are going to produce some. And we have to lose some of the NO2. At equilibrium, then, we'll have X and a minus 2X. But you can see we already have a problem here where we have two variables and only one equation. But we know that this is 35% of the total gas. So we also know that A minus 2X is equal to 35% of the initial A. This gives us that X equals 0.325A. Now we can plug this into the Kp expression. So we have our products over our reactants, and we get an answer in terms of A. And solving for A, we get our initial pressure of 169.